The broadcast is now starting. All attendees are in listen-only mode.
A very good evening to everyone who is attending this webinar today from all over the world. This is Shravani from WRI-India, your host for today. It's a new month and a new topic. So I see a lot of new faces, but most of them are regular. So I was thinking that today I will cut short on the introduction part because most of you already know about it. And also because we have a very, very important topic to discuss today, as you might have already, figured out from the title of the webinar and you have registered it for. So before starting our webinar, a little bit introduction, to what is it about. So it is a part of the Electric Mobility Forum project, which is funded by our kind supporters, the Shakti Sustainable Energy Foundation. And we've been conducting different sorts of webinars revolving around the topic of electric mobility for around a year now. And if you wish to check out our previous videos and presentation on very, very technical, highly focused topics of webinars, please feel free to check out the CityFix Learn link, where we have both the presentation and the web video uploaded for the same. So I see a lot of different countries also joining us today for this topic, and majority of them are, of course, from India. And the mix of the attendees are mostly from automobile manufacturers side, electricity distribution, charging infrastructure, and also a lot of researchers and academia and policymakers as well. So welcome everyone to this webinar. As I said, I'll cut short on the introduction part, and we all know that why is this topic really important. So I'll directly skip over to the need for the topic for this month, is because last month as well, and before that also, we have been really focusing on why is it important to take care of our batteries, because as people say, batteries are the heart of the electric vehicles, and it is very, very important to take care of them. And one of the ways is to ensure safety. And how will we do that is by knowing what are, the important factors for thermal runaway, fire characteristics, and suppression in lithium-ion batteries, because this is the most widely used technology at the moment. So we're focusing on that. So as you might have already registered for to know the key takeaways from this webinar, I will still repeat it for people who have just joined us. So we will learn a lot about different aspects of the same topic. However, namely, what is the nature of thermal runaway? What factors can affect thermal runaway propagation? What are the fire characteristics variation with different cathode chemistries? And also, what are the fire suppressants for small lithium-ion modules? Apart from that, there might be many, many interesting topics and subtopics that our speaker will introduce today in this webinar. So stay tuned for that. Now, coming to the speaker for the month, most of you have already attended one of the previous webinars who was delivered by the speaker itself, and we're really fortunate to get hold of the same speaker twice for the second time. So it is Dr. Judy Jeevarajan. So I wouldn't do much justice by giving, like such a lengthy background of hers, and she's brilliant, but I will just cut short and give you the brief about who our significant speaker is for today. So Dr. Judy is currently a research director at UL, and she has worked in the area of batteries for more than 21 years with a primary focus on lithium-ion chemistry. Also, before joining UL, she worked at NASA Johnson Space Center in Houston for 12 years. She was the group lead for battery safety and advanced technology at NASA JSC. And before becoming a civil servant at NASA in 2003, she worked on-site NASA JSC for Lockheed Martin Space operations for 5.5 years. She has a background in chemistry, and namely, she has done an MS in chemistry from University of Notre Dame in 1991, and also she had a PhD done in chemistry, specifically electrochemistry, from University of Alabama. She has also been, writing different kinds of knowledge products, and namely, she has contributed to 3 book chapters, and one of them are on battery safety, and that was published in 2009. The second was on commercial lithium-ion safety, that was published in 2014. And the third one was on safety of lithium-ion batteries in commercial equipments, which was published in October 2018. Now I can go on and on describing how brilliant she was, but let's get on to the topic and let her do justice by introducing herself and her organization a little bit more, and then coming to the topic. So this brings me to the end of my introduction part, but also I would like to give you a very essential, know-how about, the most boring part of the webinar, which is the logistical part. Thank you everyone for sending us a lot of questions in the registration form. We have discussed it together with the speaker, and we will try to take as many as we can during this webinar. But I would like to apologize beforehand to all of you if we have missed out on any of these questions, because again, you know that time is a constraint over here, right? Secondly, I know that most of you will have a lot of questions during the webinar. So I would request you to kindly, keep sending your questions in the questions box and not in the chat box, because we won't be able to see it if you put it out on the chat box. The last information is regarding the materials. So don't panic if you have missed out on any of the, key topics, if your network is bad, or if you have, forgotten taking notes, or, missed out on a key aspect due to the network issues. Obviously, these are the perks of working from home, right? Don't worry about it. Within a week or two, we will have all the materials uploaded, which includes the video and the presentation in the same link that you have registered for, which is in the CityFix Learn. Do keep checking it, and if not, do feel free to reach me out via LinkedIn, or of course, my email ID. So wishing you a very good learning session today, and handing it over to our speaker. So Dr. Judy, I'm making you the presenter now.
Thank you, Shravani. Thank you, Shravani, for the kind introduction. Good morning, good afternoon, and good evening to all the attendees. Thank you in advance for joining this session. As Shravani mentioned, I'm Judy Jeevarajan, working at Underwriters Laboratories as a research director for electrochemical safety. And today I will be talking about thermal runaway. I won't talk too much about what causes it, but I'll give you a background on that. And then I'll talk about fire characteristics, as well as mention some of the tests we've done at the lab scale on fire suppression. So the battery safety group would like to have, would like to do a lot of scientific research to advance safer energy storage. And that has been our theme for the past few years since, I started with UL. And how we go about doing this is in three ways. One is with research, the second is with outreach, and the third is by education. We conduct our research and share our scientific data-driven knowledge, and this helps to build safe and reliable, as well as innovative designs to meet the world's increasing energy demands. And we conduct battery safety summits and battery safety council forums to in an effort to outreach and to share our knowledge, as well as share the knowledge of people we know in the community, and make the battery systems and in their applications much safer. And lastly, education, where we actually participate in trainings and webinars, and also present, actually, like I'm doing today, on our research findings. And we also like to create learning modules for students of different age groups. So there are various ways in which we actually go about transferring the knowledge that we learn through our scientific research. So today, what I'm going to do is give a little bit of background on why I'm doing this, talk a little bit about thermal runaway in lithium-ion cells, and then show what we've learned as a means of characterizing the fire from two different cathode chemistries that make up lithium-ion cells. I'll talk about the fire suppression that we have used on a lab scale module, and what the results were from that, and then I'll summarize at the end. So lithium-ion batteries were first commercialized in the 1990s. And as we all know, it has the highest energy density of all rechargeable battery systems in the world today. It also does not have any memory effect. It has a very long calendar and cycle life, and it has a very good rate capability. And it's used in a myriad of applications, from consumer electronics to electric vehicles to stationary grid energy storage systems. And we also see them today in marine as well as space applications. But associated with this high energy density is also their propensity to experience fire and thermal runaway if you do not design or use them correctly. And because of the proliferation of the use of this battery chemistry, there are several hundred manufacturers of lithium-ion cells and batteries today. And not all cell designs are certified, especially the low quality ones that are also inexpensive. And some of these, are actually also low quality that they look similar to the OEMs and so on. So, so what I'm going to do today is, although I won't mention too much about the difference between the original and the low quality ones, I'm still going to be talking about what hazards can be encountered with different types of these cells. So what is thermal runaway? I looked up Wikipedia. Even though we actually write so many standards and we define the word thermal runaway, I still wanted to see what is out there when someone Googles it. So Wikipedia actually talks about thermal runaway as a repeating cycle in which excessive heat causes more heat until the operation ceases or an explosion occurs. And examples are lithium-ion batteries, and they also had germanium-based bipolar transistors. I'm trying to see if I can remove that thing on the side, but I'm not sure how to do that. Okay. Okay, good. I'll be talking about lithium-ion batteries. So I just wanted to, give the example of the germanium-based bipolar transistors here. So what happens in this case is that high temperatures cause the current to leak, heat up even more, and then eventually become unstable or self-destruct. So that's the bottom line, right? That the heat is so high and self-generated that it's uncontrollable. So the way we define this in lithium-ion standards is that thermal runaway is defined as an accelerating release of heat inside a cell due to a series of uncontrollable exothermic reactions And these were all really, small applications or low voltage and low capacity applications. But today we have, they are being used in really large applications like grid energy storage and electric vehicles and so on. So there's a bigger challenge for us now, because sometimes we are taking these really small cells and putting thousands of these in batteries and not fully characterizing, their safety and whether that single cell tolerance transferred to the larger battery size. The other thing can also be that there can be larger cells that are used but with lesser number of them, but still, there's a high voltage and a high capacity that's associated with the entire battery pack, and there is a lot more energy that is there associated with these compared to the portable consumer devices. But on the right side, I have some incidents of lithium-ion fires, and from that, what you can see is that it does not matter whether it's a small battery or a large battery. Of course, the volume of smoke and fire coming out is going to be a little different, but the extent of damage that can happen can be pretty extensive, even with the small portable devices. For instance, you see the picture here where I show an electronic cigarette that had shorted and caused damage, and you can see that people were actually hurt in that. There were burns, third-degree burns, and then you can see the damage to the couch, the carpet, the drapes, and furniture there. And this is another picture where we had several incidences of hoverboard fires one Christmas season a few years ago. Again, it's a matter of how you design and how you use it. And then we've also seen fire incidents in cell manufacturing facilities. We've seen, shops burned down. We've also seen a lot of fires in batteries recycling facilities. And these are all, things that the ones in manufacturing and recycling facilities are, of course, larger fires. But again, it goes to showing that this battery chemistry can be pretty hazardous and have catastrophic results. So lithium-ion hazards in general can be divided into three main categories. One is thermal, the other is mechanical, and the last one is electrical. All of us are very familiar with the electrical type of hazards that the lithium-ion cells can undergo, and I'll talk more about this in the next two slides. But there are also other hazards like the mechanical hazards. What happens when there's an impact and these batteries get dented or they get impacted with and have a damage to it. And then what happens when you're on a rough road and there's so much vibration that it could affect your battery module and how it is interconnected and the other systems that go around your battery and how that is affected. Is the cooling system affected and so on. Those are all, is the architecture and the design, are they affected and so on. Those are all things that we have not fully understood yet. And then when you look at the thermal side, that's a little bit more understood also, where, if it's too hot, you have decompositions of electrolyte and you have destabilization of the electrodes and so on. And then when it gets too cold, we actually increase the internal resistance of the cell because of the low viscosity that the electrolyte experiences. And then you start looking at lithium dendrite formation and so on. So in the next two slides, next few slides, I'll talk about mostly the electrical hazards. So these are really well understood ones. When you look at some of these well-known ones, the ones that come to the top of our mind are overcharge and short circuits. So overcharge, and the next two slides, I will talk about that. Apart from overcharge, we also see that there's a problem with repeated over discharges. For instance, people think that when you over discharge a battery, it just dies. But that is not always true, because you could have subtle over discharges, and that can subsequently lead to some kind of other issues where you're forming internal shorts and you have a thermal runaway at some point, even without you noticing it. Extreme thermal environments, again, like I said, it can cause dendritic formation inside, or it can cause decomposition of electrolyte that can again lead to internal shorts and so on. And then external shorts can be high or low impedance shorts, and both of them are very prevalent. The low impedance shorts, which are the hard shorts, short circuits, are the ones that we are all very familiar with, but the high impedance ones are also very hazardous. And when you look at internal shorts, these can be caused by two different ways. One is by manufacturing defects, and one is by misusing in the field. The manufacturing defects are more difficult and subtle defects that can manifest themselves as larger internal short circuits in the field during use. And the misuse in the field is anytime you do not design your battery properly to take care of all these other hazard causes, then you actually have a generation of an internal short inside your cell or a battery, and you can have a failure. So going into the overcharge hazard, what really happens in an overcharge is you can either be charging it to a higher voltage than what it's capable of, or you can be charging it at a very high rate that the cell is not capable of handling. And in both cases, what happens is that there is electrolyte decomposition, and so you start forming gases such as hydrogen, carbon monoxide, and carbon dioxide. And there can be cathode destabilization because several of these cathodes change structure when they go above a certain voltage. And so some of these, especially ones, the high energy ones like lithium cobalt oxide, can easily release the oxygen. So now you have oxygen inside your system. And also there's lithium metal dendrites that can be formed during the overcharge process that can pierce the separator. So now you have lithium metal dendrites that are formed. You have a destabilized cathode that has released oxygen. You have electrolyte decomposition that also has provided some flammable gases. And because of the high temperatures you're already experiencing from all these conditions, you can easily have venting, fire, and thermal runaway. Then going on to the overdischarge hazard, in general, when you overdischarge a cell, copper dissolves from the copper current collector, which is on the anode side, and then it deposits itself during the charging process. It deposits itself as metallic copper on the electrodes and the separator. And if you really overdischarge it to a point where a lot of copper has dissolved and gone into solution, and then later spreads itself out between the electrodes and the separator, then the system becomes an electrical wire instead of an electrochemical system. And so you have a short circuit inside the cell, which is a very benign short, and the cell dies. But when you have subtle overdischarges where you're taking it down below a manufacturer's specification, but you're not really discharging it to the level where you're killing the cell, then they start depositing metallic copper randomly through the charge process. And when you keep doing this often, then at some point you are going to develop heat because there's not enough location for the ions to move through the copper metal into the graphite to do the intercalation process. And then you also have gas production when you go to really low voltages, which can be visibly observed as swelling in pouch cells, but you cannot see that in the metallic can cells. So all these things together at some point cause the cell to go into thermal runaway, even without looking at like it's in an overcharge condition, or even without exceeding the manufacturer's limit on the upper side, which is the charge side. So this is another hazard cause that had been overlooked quite a bit in the past, but now people are realizing that there are more hazards associated with this hazard cause also, and so they've started being more vigilant. This is external short circuit. As I said, here I have some pictures on the external short showing for a 14 cell string that went into thermal runaway. It's because the PTCs inside the cell actually have a voltage limitation And when you put 14 cells in series and that PTC gets activated, it actually ignites. And so that becomes the cause of a hazard. And in my last webinar that I gave with WRI, I actually went through the details of how that happens. I described what a PTC is and what a current interrupt device is. And these are safety features that are found inside these cylindrical lithium-ion cells that have limitations that can then manifest themselves as problems if it's not designed correctly and controls are not placed in the correct location. With respect to the high impedance short, I just wanted to quickly mention that that is something, as I said before, that people don't pay too much attention to, but these are where you have leakage currents that are caused due to defects that are created because you didn't, anodize your battery container on the inside, thus causing a short circuit path between your cell and your battery container, or you didn't ground it properly, or your cables and connectors, had some kind of it got cut somewhere or scraped, and so now you have a leakage, electrical leakage path between your battery wire and your container, or your cell and your battery wire, and so on. So there are small things that cause this, but then it can become a really large hazard if not designed correctly. So if you look at standards, there are lots of recommendations that are provided on how to avoid these types of hazard causes. And I talked quite a bit about the internal shorts. Right here, I want to show you that, in general, there are lots of defects that one finds inside lithium-ion cells with on the electrodes or the separator. For instance, you might have a separator that was torn, like you see in this picture, and then, or you might have an ion particle which is not supposed to be there in one of the cathodes. And as you can see the rust-like nature there, and you can see that the separator near it has actually been affected, because in one case you see the pores in the separator, and in one case near the ion particle itself, the separator has all its pores closed, which means it has been thermally affected by this ion particle. You also see the current collector in this case, where the copper current collector has a hole in it. And then there are also, some electrodes where we found aluminum filings stuck to it, which tells you that the tooling that they were using to stack these electrodes had some kind of a contaminant that was that transferred itself to the electrodes, and this was found on literally every single electrode that was present in that particular cell. And then, of course, I have one electrode picture here that shows a very pristine electrode. And that is also possible with high quality manufacturers. You do get some really pristine electrodes. So now I'm going to start talking about the thermal runaway and show you some pictures on that. This first one is just, and also some videos. This first one is just to show you, thermal runaway with an overcharge condition. And you can see this is a pouch cell, and we overcharged it at the 1C current rate. And you can see the type of fire that you're, it's pretty big. And with pouch cells, they do not typically come with protective features. So you have to provide external protection. Most of the other thermal runaway tests that I'm going to show you today were caused by the use of a patch heater. So this first one is an NMC cell. This cell is 25 ampere capacity, and we take the cell into thermal runaway by placing a patch heater. The patch heater actually went over the entire side of the cell. And in this first case, what you will see is that this is the first venting of the cell. And you can see a lot of smoke that comes out, but we do not see any fire in this case at all. So the second one here I have is an example of a lithium iron phosphate cell. And what we found is that there was a variation in the behavior of the cells. In the first case, this one that is going on, we saw fire and smoke. Of course, the first, initially we see the smoke coming out, but then in a few seconds, you will see the fire also. So that was a pretty big fire there. So in this second case, which is, these are cells from the same module that we took out to do our tests. And in this particular case, we saw only smoke. We did not see a fire like we did with the previous one. So again, this tells you that even within cells from the same lot, you could have cell-to-cell variation. And so one needs to make sure that we are actually understanding the worst case situation. Just showing you the plots for this NMC cell that you saw, the first one which had just the smoke. We had the heater that was placed on one whole side of the cell. Because it's a 25 ampere cell, we needed to use a heater that would cause the thermal runaway to happen, and we had 3 thermocouples. And as you can see, when the first venting takes place, we see a drop in temperature, and that is how we know that the cell has vented, and we can coordinate this with the visual video that we are looking at. And then we see that at the point of thermal runaway, there's a shoot in temperature, and it really goes to very high temperatures. And as the as the cell releases its contents and the smoke, then the temperature starts falling off. So we call the vent temperature was about 200, and the TR, which is the thermal runaway, had started at about 213 degrees C. And for the LFP cell, for the same thing, you can see that in this case, the temperature dropped a little bit here. That is the venting temperature. And then the thermal runaway temperature is right here. It's about close to about 200 degrees C in this case. And here I have some videos for the module itself. For the NMC module, we had 3 cells in parallel, as you see here. And we had heaters here on 2 sides of the cell. And we had 3 cells, as I said here. The center cell was the trigger cell. And in the case of this particular NMC module, we saw both fire and smoke. If you recall the single cell test, we saw only smoke. But in the case of the module, we saw both fire and smoke. I'm going to move it forward a little bit so we can see it faster. So that's the fire from the NMC cell. And then here I have the LFP modules. One module of the LFP cell had only smoke. And then the other module of the LFP cell had both fire and smoke. So the interesting part about this was the way they react in the beginning is quite similar, where they all give out the same volume of gas, and the components are obviously the same. But for some reason, one of them, just results in a smoke, and we see a lot of stratification of the gas on the bottom of the module, but it does not really go into a thermal runaway. I mean, it doesn't actually get converted into a fire, but in this particular case, you see that it does get converted into a fire. Here we have the battery level. In the first case with the NMC battery, we see fire and smoke. This was a battery that had 4 of the banks in series, so it's about 15.2 nominal voltage. And of course, 3 cells are in parallel, so we have 75 amp hour capacity. For the LFP battery, we had the same voltage, slightly higher capacity because we had 15 cells in parallel per bank. And so it's about 82 amp hours. So you can see that had a very big fire. In the case of the LFP, we actually had to use about 8 heaters on the cells to cause this to go into a thermal runaway. The design of the battery is such that if one cell only is heated up, it does not go into it goes into thermal runaway, but it doesn't propagate to the other cells. And what we wanted to do was to do a worst case to find out, how it behaves under a worst case condition. So we had about 8 heaters to make sure that the fire actually propagated. And here I have some information on the gas composition very quickly on the cell level. NMC cell, as I said, it's a 25 amp hour cell, and a single cell released about 41 liters of gas. And you can see on the right side the components. The carbon monoxide was higher, and of course it's much higher than the lower flammability limit. And hydrogen was also high in this case. But what we have here is a lot of carbon dioxide and carbon monoxide, almost I would say, you could say in an almost same ratio. What we had observed in this case was mostly smoke. So what I'm going to show you in the next one is what happens when you have a fire and a charring of your cell, where almost all of your cell components have reacted. This is a 5.5 amp hour cell, which is an LFP cell. And what we found from a single cell is what we got from a single cell was about 3 liters of gas. And in this case, because all of the material was charred and reacted, we find much higher composition of carbon dioxide and almost no carbon monoxide. So the first thing that comes out of a lithium-ion cell when you have a breakdown of the electrolyte is carbon monoxide, and because these are all carbonates. But then when they mix with oxygen, they become carbon dioxide. And in this case, what we see is a carbon dioxide that is present, but no carbon monoxide. And we also see a really high percentage of hydrogen, which again is a real concern because it's, the LF is 4%, and we had about 54% of hydrogen that was released from this small cell. And then we have other flammable gases that were also released, like methane and ethylene. Just quickly showing you the analysis for the battery packs, NMC and LFP. One thing I did want to point out to you here is that these were collected using the cone calorimeter. The previous ones on the cell level was actually done in a chamber in a very restrictive environment, so we know exactly what the volume of gas that was released was. In these cases, because it's in an open chamber, in an open environment, and we use a cone calorimeter, so the amount of volume that we are measuring is an approximate number. So as you can see, we have an estimate on the total amount of hydrocarbons, carbon dioxide, which is huge, and also carbon monoxide, which is also a huge volume. Going to the LFP, because the battery was it was enclosed in a box. So the only thing that we detected from the smoke that escaped was the total amount of hydrocarbons. We could not detect anything with respect to carbon dioxide or carbon monoxide, but we'd also detected the hydrogen gas. So I wanted to quickly mention one of the challenges that we see with gas composition analysis. HF, which is produced in really large quantities, is really not easy to detect because it condenses on the walls of the chamber and the pipes. And there's a group in in Sweden at Chalmers University, where Professor Melander and Dr. Larson have actually carried out these experimental studies and showed how much HF can be produced. HF is both toxic and corrosive, so that's something that people need to keep in mind. Another thing that we found out more recently with the Arizona Battery Energy Storage System fire is the presence of HCN, which is hydrogen cyanide, which was much above toxicity limits. And we know that lithium ions do not produce cyanide, but what we found is that the plastics that are used in the system making up the battery actually produces cyanide. So when you look at the way you build your battery packs for vehicles, you need to keep in mind that whatever is released goes into the passenger compartment of the vehicle, and so you need to make sure that cyanides are not present in the products that you use to build your battery packs. But going back to HF, we also need better analytical methods to determine the HF concentrations. So quickly going over our lab scale fire suppression studies. The way we did the experiments was we had 9 cells in parallel, and the cells were all physically in contact with when you look at the picture on the right, you can see that pretty much all the 9 cells were affected by it. When you look at the late release water mist, what we found is that in this particular case, we were actually able to control the fire, and all the flames were contained within the box. And if you look at the temperatures, you can see that they are not very high. They were, I would say, less than 150 degrees C. In the video inset, you can see, the smoke coming up, the fire, but then with the water being released, only 1 cell expels its contents, and all of the other cells remain intact. With the early release, just one more video here. Here we had a single cell that went into thermal runaway, and we did not see any flames outside the box. And as you can see from the photos on the right, that single cell does expel its contents, but the rest of the cells looked fine, and that single cell also reached high temperatures, but the others did not get to very high temperatures. And here I'm just showing you the plots for this fire extinguisher that we used, the Statex one. It's a potassium carbonate type. And so when it is released, it is not a toxic compound, which is what I wanted to show here, that it's a type of fire extinguisher that is environmentally safe too. So with the early release, what we found is that there was a short fire that we saw outside the box, but in general, the whole module had burnt up completely. As you see from this picture, there's only shrapnel that is left from inside the container. With the late release, what we found is that we could actually control the fire. There was a very small fire that we saw outside the box, but in general, it propagated only to 2 cells, and the rest of the cells were saved. But it does, the center cell does go into thermal runaway. But when we use this particular one at the right time, then we are able to control the fire. So to just summarize these, wanted to show you that with the baseline, we did have a flame outside the box and it's a sustained fire. With the water mist, which was very early, then we had a flame outside the box, but with the late water mist, we did not. And we also looked at different sites, and you can see that the results we have are quite different. So again, this goes to point out that you've got to do it for your environment and your design, and not just generally look at what people are doing or what their results are and decide that that's going to work for you. And with nitrogen early and with late, we had, in one case, it was the early case, we actually were able to put it out. But in the late case, even though it doesn't come out, it did propagate to all the cells internally. With the Statex, we actually found that there's a big fire at the beginning and at the end. But with the late one, we did not see a fire that came out of the box itself. So to summarize, what I wanted to say is that thermal runaway can occur due to different types of hazard causes, and some of the main ones that you can categorize them into are electrical, mechanical, or thermal in nature. And it's very important to fully characterize the system under all the credible off-nominal conditions. And this will help you to understand why your limits are for your battery design. And so you can put your controls and limits there, and also recommend what the usage limits will be. And then carrying out a high fidelity thermal analysis actually provides a lot of data. Here, what I say very generally is it will help you to design appropriate heat dissipation paths. But what it really also tells you is, where you can put your thermocouples so you can get the worst case temperatures in your particular battery pack. It can also tell you what your thermal gradient is within your battery pack. And so if you start seeing larger deviations or larger thermal gradients, then you can start looking into how to design it better or how to save your battery. And the events accompanying thermal runaway can vary quite a bit. We saw venting or fire or smoke, or sometimes all 3 of them. So, or sometimes, 1 or 2 of them. So that is something that you need to understand for your system. And what you saw was also even cell-to-cell variability within the same battery pack. 1 cell went into thermal runaway with a fire, 1 cell had only smoke. So these are things that we need to keep in mind and design for the worst case. Toxic and flammable gases are released from lithium-ion batteries and battery systems. And so the data that you get on the gases that are evolved from your particular battery type should be analyzed for the volume of the chamber or the confined space that these gases are, that the battery is located in, which is where the gases are going to be released into. And that way you can understand what your flammability and explosive limits are and what this particular battery can cause. It also goes to toxicity levels. And this will also help you to design the vent system appropriately. And lastly, I wanted to mention, as you have seen, we've looked at really small modules, 9-cell modules, to study some of the fire extinguishing, suppressants that some of the different suppressants that we've studied. But what I would like to say is that this particular area has really not been optimized. Fire extinguishing methods need to be studied further, and you need to look at the size and the nature of your battery. If you have a battery that's fully enclosed, then you need to find a way to get to the trigger cell where the fire initiated, so you can cool down that and the neighboring cells that had reached higher temperatures. That's the only way you can put out a fire, especially with lithium-ion, because it can self-generate the oxygen, the heat, and with the organic solvent also present, it can actually cause a fire without having outside air at all. So in conclusion, I would like to really thank Dr. Pravin Gandhi and Alex and their team that did an excellent job on these fire tests, as well as the fire characterization tests, as well as the suppression studies. These were all done in our UL Northbrook facility with the help of their team. And I would like to thank Dr. Yuvraj Robles in my team and Saad Azam, who helped with conducting several of these tests. And Saad is currently at Dalhousie University with Dr. Jeff Don, just starting his graduate school studies. And I would like to thank all of you for listening. And now I'm open to questions.
Thank you so much, ma'am. It was a wonderful session and you very beautifully explained each and everything. I know it is injustice to make you explain to such complicated things within a very short time span. However, we tried our best. So without wasting much time in my speech, I will jump into the questions. So let us take the first question. Is the lithium-ion battery safe for electric vehicles today at high power and heavy operating conditions? So over to you.
Sure. Of course, any system that has energy is prone to energetic reactions. We've seen that with gasoline vehicles. When we first had gas-powered vehicles, we had a lot of accidents and incidents and fires. Same thing goes with lead acids. People have actually, lost parts of their body, lost lives because of the hydrogen that is released from lead acid batteries. Of course, today we have the seal lead acid, so they're better. And the same thing goes with lithium-ion. So lithium-ion, of course, is highly energetic. It is capable of, producing fire. It is also, as you saw, capable of producing gases that are flammable. So the bottom line is for us to understand it and to design it safely. And once we do that, and of course, like I said, everything is different. You just can't say this design works for all batteries or all systems. So as long as one can characterize it fully, understand the limitations, and make sure that the safety controls are in place, then the battery system is the best that you can see at this time for these high power and high energy applications.
Okay, ma'am. Coming to the second question, what is the importance of analysis of thermal management systems in electric vehicles?
Yeah, I mentioned that quite a bit. High fidelity, see, when we say thermal analysis, there are many ways you can do it. You can put a ton of thermocouples like we actually do nowadays, but in our research, but ours are small battery modules, right? So we can put any number of thermocouples to study it. But when you look at when you start getting into really large systems like battery packs for electric vehicles or for stationary grid, it's not possible to put that many and have a decent, analysis. So what we recommend is a thermal analysis or a modeling study. You create a model and you start looking at, what comes out of it. But the data that needs to go into the model should be based on experimental data. So you can build small modules, take the data, and then put it into your simulation and model, and then look at expanding it to larger systems. And then you go through several iterations to find out what the thermal gradient is in your battery. And once you understand the thermal gradient and the areas where you have issues, then you can start looking at cooling systems and also looking at the environmental temperatures. For instance, one part of the battery may be near your electric motor. One part of the battery might be, at a place where the external environment is really cold, while the other part is near a hot component, and so on. So you need to understand what that gradient is also, and keep it to the minimum. For in my previous job for space applications, the requirement I used to give was 3 degrees C as your gradient for the entire battery pack. So you can see what that takes. But that is how you keep your system safer, is by reducing the gradient on your battery pack. And that way, you can make your battery safer, and it will also last longer, because you're not deviating in voltage and capacity because of the heat that is produced unevenly. So that is what I would recommend, that thermal analysis and understanding the thermal dissipation paths and making the dissipation paths more efficient will actually help a lot in not only the safety, but also in prolonging the life of your battery.
Okay, the third question is quite an interesting one. It is about the standards. So the person asked, what are the special considerations and relevant standards for fire protection safety? Which, again, a link question to that, which UL standards that are used and discussed here, and are those applicable in all lithium-ion battery chemistries? And also, they ask if there are any open source softwares for the safety analysis.
Okay, just the last part, there's no open source for safety analysis. There are some programs that are platforms, I would say, that have come about that can do, that can process large volume of data, mainly because, we are manufacturing millions and billions of cells, and 2 years later, we found out that cell that was produced 2 years ago had a problem. It's because it takes time to analyze all that data. And so platforms are being built today to understand or to process a large volume of data in a short period. Same thing goes with analyzing, whether a problem is going to happen. Looking at the data and figuring out whether a problem is going to happen in a particular battery. Again, there are some platforms that are working on it, but I don't think there's any open source at this point, open source software at this point that can do that for you. Then going back to standards, there's only one fire standard which I know, which is the NFPA 855, that is mostly associated with grid energy storage systems. If you look at electric vehicles, I think that's still under development. I have not seen from the SAE side, which is the Society of Automotive Engineers, that they have any standards for fire safety. But I have what I have listed here is the safety standards that are in existence today for electric vehicles. As you can see, there's a report that from Sandia National Labs, from the Freedom Car DOE program, that talks about what you could do in terms of the test methods that you can employ to understand the worst case failure modes of your batteries for electric vehicles. And then there's also the J2464 and J2929 that talks about the safety and abuse testing for EV batteries, and also there's a safety standard for lithium-based rechargeable cells. The ISO has 2 documents. Of course, UL has 2 different documents. For one is for the cell itself, which is a standard for lithium batteries, that it looks at both primary and rechargeable cell level testing. And then the 2580 is for batteries for use in electric vehicles, where you look at the pack, subassemblies, and modules in a motorized vehicle. And then there's IEC standards. Again, the 62133 goes to small cells and battery packs, but we also have the 62281 that is looking at safety of primary and rechargeables during transport. And the United Nations one, again, is for transportation only. Again, when you have to transport your the modules or your batteries even for electric vehicles, then you have to make sure that you follow the 38.3 rules. And then the IEEE has some lithium battery standards. Although these are not for electric vehicles, they're just listed here for typical standards that people would use to understand the batteries and in portable devices, etc. Or even batteries that are smaller batteries that are used inside your electric vehicle, in the electric vehicle for other applications. So these are the main ones that I've seen. There are also other standards like the UL 9540A, which talks about how to do a thermal runaway propagation test. And that is something that is written for the grid energy storage system, but one can adapt that same thing for an electric vehicle to understand how to go about triggering a cell into thermal runaway and looking at the propagation to other cells in the battery pack.
Thank you so much, ma'am. This is really, really useful. I think most of the audience will also agree with me that this is something that they might be looking for, and this is quite a good information. So coming to the fourth question, what is the present rate of failures in EVs because of thermal runaway in lithium-ion batteries?
What I have, the latest official document that I had from the National Highway Transportation Safety Authority was completed in 2017. And that's the most official document that I have, or the latest official document that I have. And in that, they had reported 41 electric vehicles in 2017 that had experienced a fire. So if you look at the percentage of electric vehicle fires, it's actually really small compared to the number of gasoline fires. And comparatively, for that same report, we had close to, it was reported that there was close to about 93,000 gasoline power vehicle fires. So when you do that comparison, you see that electric vehicle fires is really small. But you've got to remember that the number of electric vehicles that was out in 2017 was really small, and every single vehicle that went into that had a fire actually was reported. I mean, it was reported in the media, and a big thing was made out of it. So I would say at this point that we do not have a good, feel for what it's going to be like. Only when we start getting more in the on the road will we understand better, how many accidents are going to happen, and because of the batteries, and how safe these are. So I would say it's a little premature for us to understand fully or comprehend fully how bad these are going to be on the road.
Thank you, ma'am. The next question is particularly really interesting for me because even I belong to a state where there are different kinds of calamities like flood. Honestly, people are constantly addressing, concerns about battery safety only related to temperature, but sometimes we forget to mention about, how is it going to get dealt with different kinds of natural calamities. So this question relates to that, and the person asked what kind of battery safety we require during very bad or like flood conditions. So this is not only for the northeastern states, but also mega cities like Bombay and also Kerala that constantly keeps on facing flood. And they also have adopted a lot of electric buses currently. So just wanted to know the question that how do they deal with it? And the link question is, how about the battery enclosures and its accessories? And how do they play different kinds of role in those types of environment? So
sure. So depending on the type of flood water, which I think mostly is saline, but again, it depends on, where you're getting your floods from. If you have a saline, flood with a flood with saline water, you are going to get a short circuit. And remember, these batteries are high voltage. So you're going to get a really big arcing. And when you have arcing, that causes a bigger fire than just, a simple short circuiting or another type of event. Because arcing can actually melt very high temperature metals. So you have a bigger problem. So what I would say is, depending on the environment, the enclosure that you use to build your battery is very important. Most of the time when we have, a requirement to prevent ingestion of water into your battery pack, we use a sealed system. But when you use a sealed system, you also have to have a vent capability and make sure that the vent or the rupture disc that you're using in your sealed system is working correctly, because you don't want an explosion, but a controlled vent when there's something that is going wrong. So that is the main thing that you need to take care of. Make sure that the enclosure that you're building is watertight and has the right venting capability in the event that something else goes wrong. The other thing that you have to also look at is how you design your terminals. So your battery terminals, in general, electric vehicles, have battery terminals that are well protected. And they will be, encapsulated in a material that prevents that type of arcing. So you need to make sure that the enclosures that cover your terminals, do not melt or do not get degraded due to environmental conditions. And that is something you can actually physically check, because those are typically visually observable in a vehicle. So one thing is you want, because your terminals are high voltage, first of all, you don't want them, exposed, because you could have arcing when the two of them are close to each other. The second thing is these types of other issues like flooding can cause additional short circuits and arcing. So designing your terminals well and protecting your terminals well and designing your entire enclosure to be waterproof and airtight will actually help a lot with keeping your system safe, especially in the case of flooding and so on. And these systems can also sometimes protect you against extreme temperatures too, because they are one level of protection against the external temperatures when you build something that is strong, that is also sealed. So I hope that helps.
Yes, ma'am, very useful. And I hope people from all these states are listening to you very carefully and, are able to adopt all these suggestions. So coming to the next question, what are the battery pack design considerations keeping thermal and fire separation behavior as design constraints? Hello? 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 Ma'am, can you hear me? Hello? Hello, Rindu. Hello? 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 Hello, Rindu. Hello?